A massive hot anomaly is looming over New York, linked to forces that once divided continents. Imagine standing above a colossal, ultra-hot region deep within the Earth, one that has the potential to reshape our understanding of geology. This is exactly what researchers have uncovered. A fresh study, published in the journal Geology by scientists Thomas M. Gernon, Sasha Brune, Thea K. Hinks, and Derek Keir, unveils details about a significant mantle anomaly, a geological feature characterized by abnormally hot and low-density rock lurking beneath New England. Referred to as the Northern Appalachian Anomaly, NAA, this intriguing structure spans approximately 400 kilometers and is located around 200 kilometers below the surface of the Earth, nestled within the asthenosphere. This upper mantle layer transitions between solid and molten rock, making it not only fascinating, but also vital for understanding geological mechanics. Using cutting-edge geotectonic reconstructions and mantle flow simulations, the researchers determined that the anomaly isn't a recent development. Rather, it is a remnant from the Labrador Sea rifting event that took place around 85 to 80 million years ago, during the late Cretaceous period. This begs the question, what is this anomaly's journey to New York City telling us about the geology of our planet? A geological instability with a history. For years, geologists grappled with understanding the NAA through the lens of edge-driven convection. This concept suggests that the temperature differences between oceanic and continental lithosphere lead to vertical currents in the mantle. However, a significant issue arises. The Atlantic passive margin, located at the eastern edge of North America, has remained tectonically inactive for an astounding 180 million years, far exceeding the expected lifespan of such convection processes. The new study boldly proposes an alternative explanation. The anomaly might be indicative of a Rayleigh-Taylor instability. This geological phenomenon happens when a lighter, buoyant layer of mantle rock rises through a denser, cooler layer sitting above it. Such instability likely originated during the breakup of the Labrador Sea, the time when North America and Greenland began to drift apart, stretching and thinning the lithosphere. Once this upward movement of hotter mantle rock kicked off, it transformed into a self-perpetuating feature, gradually moving west-southwest at roughly 22 kilometers every million years. Interestingly, the authors point out that this speed aligns with predictions from global-scale mantle convection models, indicating the movement is not random, but guided by deeper mantle dynamics. A twin anomaly beneath Greenland. Perhaps the most convincing evidence pointing toward the Labrador Sea's influence comes from seismic imaging conducted beneath north-central Greenland. There, researchers discovered a comparable mantle anomaly, mirroring the size, depth, and seismic velocity structure of the NAA, suggesting these two features likely originated during the same tectonic event. The symmetry points to a larger narrative, where both anomalies emerged as remnants of a significant upwelling event that unfolded across the rift zone. As the Labrador Sea split apart, these geological instabilities likely formed on both sides of the separating landmasses. While the Greenland anomaly has remained relatively stationary, the NAA has journeyed considerably across the North American tectonic plate, traveling thousands of kilometers over millions of years. Additionally, the study identifies the Central Appalachian Anomaly, located further south, as a potential younger sibling of the NAA, signifying an earlier stage in the same migration process. If this hypothesis holds true, it could imply that mantle instabilities happen in sequences, creating a series of thermal anomalies that chronicle the history of deep mantle activity. Chapter Implications for Tectonic Stability. While the NAA poses no immediate threat to those living in the area above it, its existence raises challenging questions about our traditional views on the tectonic stability of eastern North America. Typically, the eastern U.S. is considered a geologically calm and structurally stable region. However, the notion of migrating mantle plumes or instabilities beneath the Earth's crust complicates that picture significantly. Over immense geological timeframes, such upwellings can weaken the lithosphere above, modify volcanic activity, and potentially, in extreme instances, contribute to continental rifting, the same force that once split apart the supercontinent Pangaea. In the words of co-author Sasha Brun, the NAA and similar anomalies are a legacy of continental rifting and breakup, indicating these features are not isolated, but are part of a grander, ancient geodynamic narrative. Gaining a deeper understanding of how and why these anomalies move is critical for predicting how continents may evolve over tens to hundreds of millions of years. This is particularly pertinent as mantle flows interact with major Earth processes like plate tectonics and hotspot volcanism. What do you think? Is the stability of eastern North America being redefined? Share your thoughts. Do you believe there are hidden dangers beneath the surface, or is the traditional view still valid? Let's discuss.